Okay, so today we're going to talk about three different physical quantities that get used in physics. These three quantities are used semi-regularly, particularly at the beginning of most physics classes when dealing with kinematics, which is where we're going to start our course. It's important to know the difference between these three physical quantities and when to use them. You need to know about each of them. What's specifically important is when do you use distance, when is position important, and what is displacement and when should it be used. Each of these three quantities are different, and some of their definitions might be familiar to you, but since they are different quantities and they get used at different times, it's important foundational knowledge to have moving forward. So we're going to start with distance. So distance, you can see, is the measurement of the amount of space you travel through. Okay, so distance is one of those things where it's like, oh yeah, I know what distance is, but when it comes down to it, it's kind of hard to actually give it a definition. Distance, if you think about counting steps, okay, think about counting steps. Think about what a pedometer does. Okay, so you're counting the steps. How many steps does it take for you to get from one place to another? That's one way to measure the space between two objects, specifically the space that you travel through, and that is an important distinction that we need to make. In physics, though, we're not going to be counting steps. We're not going to be counting steps. Usually what we're going to be doing is we're going to be counting meters. Okay, so meters are the units for distance. Okay. It's important to know what the units are. If I tell you to go 5 meters, that's a certain distance. If I tell you to go 5 miles, that's a very different certain distance. So those units are important. Units on just about every physical quantity that we talk about are super important so that we understand the magnitude and the scope of what we're talking about. So let's take a look at a couple of distances. So here is a map with some driving directions. This is a map that's going to get you from the Neshaminy Mall, point A, to point B, Bensalem High School, to locations that you're probably pretty familiar with. You're probably also familiar with the fact that there are many ways to go from the Neshaminy Mall to Bensalem High School. And so two of them are shown here, one in sort of a reddish-pinkish color and the other in sort of a bluish-purplish color. The bluish-purplish color is a distance traveled to go from one place to the other of 3.32 miles. Now, again, we are keeping track of how many miles we travel through on our way from one location to another. The pink one is 2.94 miles. So we have a different distance traveled here, yet we start at the same point and end at the same point. And that's where the idea of distance, we run into some problems when we try to use it in physics. It's a little bit subjective because we're talking about two different paths. Okay, so because there are many paths, not just two, in this case two, but since there are many paths, it's a little bit subjective when we talk about the distance between the Neshaminy Mall and Bensalem High School because we don't know what path we're talking about. So distance is not a physical quantity that we use too often. There are some similarities between distance and another important physical quantity that we're going to talk about, but we generally don't use distance as often in physics because of this subjective nature where the path that you take is important in determining the distance. So in order to get to a better physical quantity, we do need to define some other things. So let's move forward and talk about position. So position is your location relative to some reference point. And this idea of a reference point is going to be very important for us in physics here at the beginning of the school year. So I want to look at two more situations that you should be familiar with where you've done this numerous times. You have used reference points to determine positions in many occasions in math class. So the number line is a great example, and then the Cartesian coordinate system is another great example. So what you can see here is that if I were to put a dot here, you would be able to tell me that I'm at a position of 3. 3 is my position. So this red dot is position 3. Now what we can see is that 3 is based on where this 0 point is. Okay? And to the right of this 0 point are all positive values, and to the left of that 0 point are all negative values. So if I were to put a dot right here, you would tell me that the position is -2. Now based on the positive and negative, I know what direction to go. So that means that position is a vector. Okay? A vector is a quantity that has both a magnitude, meaning a size, but it also has a direction. Okay, so I know that I should go right or left based on the value +2 or -2. We also do this with the Cartesian coordinate system. In this case, our reference point is the origin. The nice spot right here in the center tells me that this point right here is 1, 2, 3, 4, 3. Over 4 and up 3. 4, 3. Both those numbers are positive, therefore I know to go to the right and up. If I were to give you a negative value first, you would go left, and another negative value, you would go down. So these positions are based on these special reference points, the 0 on the number line and the origin on the Cartesian coordinate system. So this idea of a reference point is something that you've used many, many times. Let's look at how we could use that going forward. So let's go back to our map here. And what we could do is I could actually draw a nice Cartesian coordinate system right through here. And we could actually define kind of where this Turnpike 276 marker is as our origin. And we could define a position for the Neshaminy Mall and a position for Bensalem High School. Okay, the Neshaminy Mall could be something like, I don't know, 1.0 negative, go over to -1.5 and up to +2. Negative 1.5 miles, 2 miles. Bensalem High School could be over 1 mile and down 1.5 miles, perhaps. This would be negative. You can see how we can define where each of these two locations is based on this specific reference point. We're using this point sort of as our starting point for how far we go in each of the relevant directions in order to get to the position that I want to get to. Okay. So now that might bring us to sort of our next point, where I want to talk about displacement. Okay, the displacement of an object is its change in position, how an object's position changes. The way we discuss change in position, the way you would determine mathematically a change in something is you would find the difference between what it was before and what it is now. Displacement is found very similarly. We take a final position and we subtract from it the initial position. And this tells us how much our position has changed. Displacement, sort of an equation for this. Displacement is denoted as delta x. We use x for positions. The delta, the little triangle in front there, denotes change in, so that would state change in position. The change in position would be equal to the xf, which is the final x position, minus XO, where we denote the word initial with the letter O, sort of as a subscript there. So we can determine the change in something's position based on where it is at the beginning and where it is at the end. You'll notice that in the equation there's nothing having to do with what happens in the middle. And this is where physics likes the idea of displacement a little bit better than the idea of distance. For the most part, the middle is somewhat irrelevant. We really just care about where did you start and where did you end. So again, let's look at an example. So here's our number line, and just a very simple example. Let's use the 2 points we used before. Let's say I started at a position of 3, and I moved over here into a position of negative 2. Okay, so from 3 to negative 2, my position has changed. Now, how much has my position changed? Well, we can use our formula to figure that out. Delta x is equal to xf minus xo. Okay, so xf is going to be negative 2. This is my xf, and this is my xo. My final position, negative 2, minus my initial position, 3, tells me that my displacement, or how much my position has changed, is negative 5. So my position change is negative 5. My displacement, how far I am from where I was at the beginning, is negative 5 units. Now, negative 5 is, in this case, it's sort of the distance. I could also have just counted my steps and said, I moved 5 steps. In this case, I moved 5 steps to the left. You'll notice that when we talk about distance, distance doesn't have a direction. Distance doesn't have a sign. We don't talk about positive and negative. We say the distance from 3 to negative 2 is 5 steps. The displacement for an object that moves from 3 to negative 2, though, is negative 5. So let's look at a more cohesive example, one that brings in something a little bit new. So here I have a number line set up, and what we're going to try to do is we're going to try to determine, for kind of a simple problem, what was the initial position, what was the final position, what's the displacement, and what distance did this object travel. So in my example, I'm going to have the object start over here at position 4. I'm going to have it travel like this, all the way over here to negative 3. Okay, and then I'm just going to slide down here for a second, and I'm going to have it slide back this far. Now, how does this work? How is this different? Well, let's kind of see if we can fill some of this stuff in. 4 is my initial position, so I'm going to put xo equals 4. I ended up, like the very end here, at negative 1. This would be xf, negative 1. Delta x is something I can calculate using both of those values. So those two things that were easy to find, my initial and final positions, can help me find delta x. And remember, what we said, what happened in the middle is sort of irrelevant in this case, because all I want to know is how far away am I from where I started. I started at 4, I ended up at negative 1. Well, what is that? What's the change there? So delta x is going to be negative 1 minus 4. Remember, it's xf minus xo. Negative 1 minus 4 is, again, negative 5. Just a coincidence. But I am 5 units away to the left in the negative direction from where I started. Now, what about my distance? If we go back to the definition of distance, we talked about counting steps. Well, how many steps did I actually take? I took 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. The distance I actually traveled was 9. Now, you'll notice that my distance in this place is different than my displacement. They're not the same value. It's not even the sign that's different. But we also have a different value. Now, notice what happened. When we calculated delta x and we kind of said we didn't care about the middle, these 4 steps right here sort of disappeared. Those 4 steps kind of seemed irrelevant. What you'll notice is these are 2 steps in the negative direction, and these are 2 steps in the positive direction, and they sort of balanced each other out to not matter in our displacement calculation. They were steps, though, which means they must be counted in our distance calculation, or the counting of our steps. Okay, so this is sort of a common way that you might see these kind of problems. One way to think about how this works. So if we look one more time over here at our map, I do want to add another path in. I'm going to add a path in, and I'm going to add the path in that goes sort of as the crow flies from the Neshaminy Mall directly in a straight line to Bensalem High School. So now what we have is we have 3 different paths. 3 paths. Each path has the same initial position, so they all have the same XO. Each path has the same final position, XF. Each path also, in this case, has the same delta X. Remember, delta X is just XF minus XO. And if both of these are the same, then that means delta X is going to be the same also. What is different about all three of these paths is the distance. The distance that I would have to travel to go from point A to point B over these three different paths is different. And that's an important distinction that we need to be okay with. Okay? I could, again, put that Cartesian coordinate system, lay it over top of my map here, and give A and B some coordinates, and then I could actually use the distance formula to find the shortest distance between them. Let's remember that the shortest distance between 2 points is a straight line. So if you can imagine a crow flying straight overhead above all of these other streets and buildings and fences and all those other things, or a ghost that can fly through things, then we can see that the distance for the third path that I've drawn in would actually then be equal to the displacement of the other two. Okay? All three of them have the same displacement. They have the same initial and final position. The three different paths, though, all travel different distances, the shortest distance of which, in this case, is the displacement of all three of them.